Hello, I am Heba Ali and I am a PhD student in the Civil and Environmental Engineering Department at RPI. And this is my colleague, Alyssa Rich Tarek, and she is a master's student in the same department. Today, we are going to be introducing the first lab in our Intro to Geo course, and it's the Sieve Analysis Lab.
The sieve analysis test, also called the grain size analysis or grain size distribution test, is a method of classifying granular soils. A series of sieves are arranged with increasingly smaller openings to assess the distribution of particle sizes that are retained on each sieve, from number 40 to number 200. Today, we will be showing you the mechanical method, and we will use this sieve shaker. From this test, you can draw an approximate particle size distribution curve. This helps us calculate the percent of soil particles that fall into the gravel, sand, and fines categories, and how well distributed across these categories the particles are. To classify a soil with a lot of fines, however, we have to do a separate test, and I know you guys are excited to see us in the lab next week for the Atterberg limits tests. Heba and I are joined today by the lab supervisor, John Lapointe, who is in charge down here, and he has prepared 2 soil types for us to test today. The equipment that we're using today is this mechanical shaker, a bowl for the soil, a digital scale sensitive to 1/10 of a gram, a dustpan and a large brush, 2 data sheets, a Sharpie, a riffle box splitter and this large pan, the 2 soil types, thoroughly dried, 2 smaller sample pans, a small spatula, a fine-haired brush, and a coarse-haired brush, and the stack of 8-inch diameter sieves with these numbers shown, including the lid and the pan. Here's our full workspace.
We will be using 7 sieves that are stacked in a descending order with respect to the size of the openings. The sieves we will use range from sieve number 4 to sieve number 200. The larger the number, the smaller the diameter of the soil particles that can pass through. At the bottom, there is a pan to catch the remaining soils. We remove the cover, and the first sieve is the number 4 sieve. This sieve has the largest openings at 4.75 millimeters. Next is sieve number 10 with openings of 2 millimeters. As you can see, the openings are smaller. Then we have sieve number 20, which has even smaller openings at 850 micrometers. Sieve 40 has openings of 425 micrometers. As we go down the stack, the openings get smaller. We can compare sieve number 50 at 300 micrometers to sieve number 100 at 150 micrometers. The last sieve we have is the 200 sieve, which retains the soil that is no smaller than 75 micrometers. Now we will start cleaning the sieves. We use the coarse brush on the number 4 through number 40 sieves. The number 4 sieve allows a particle with a diameter no larger than 4.75 millimeters through. If this sounds familiar, it's because this is the boundary between gravel and sand. Anything bigger than this is gravel. The number 200 sieve allows a particle with a diameter no larger than 75 micrometers to pass through. We use the fine brush on the number 50 through number 200 sieves. This represents the boundary between coarse and fine particles. And anything below this sieve is fine-grained soil.
Okay, next up is weighing the sieves. After we clean the sieves, we must weigh each of them and record the weights on our data sheet.
So the sheet will have the sieve number, the sieve diameter, and the weight of the empty sieve, which we are going to record right now.
So we're going to take the first sieve, which is sieve number 4, and we're going to simply put it on the scale, easy peasy, and just weigh it like that.
It doesn't really fit on scale or
Yeah, we can do it like that.
No, that's
so silly. This is like.
No, it's moving. We need a bigger scale.
Okay,
We probably didn't use this for the...
No, but we can put something on top of it, like a little...
And tear, yeah.
Yeah. So what we're actually going to do is we're going to take this piece of cardboard and we're going to put it on top of the scale. And we're just going to tear the scale with the cardboard on top so that we can put the weight of the sieve on the cardboard without measuring the weight of the cardboard as well. So we can take our number 4 sieve again and we can put it on top. And you can see that it fits on the scale, easy peasy. And that's how we're going to weigh each of the scales every time for the rest of this lab.
So we write down number 4 sieve, 4.75 millimeters diameter, and now 750 grams. Let me move closer so you can see those 3 colors.
This is used as a comparison so that we can calculate how much soil is retained on each sieve after the test. Okay, so now we're going to weigh approximately 800 grams of a representative soil mixture so that we have enough soil to run 2 samples through the shaker. The way we're going to measure this 800 grams is by taking this bowl, which is 173 grams, and zeroing the scale. This will allow us to directly measure the weight of the soil. Then I'll carefully pour it into the bowl to try to get around the 800 grams. So we're approaching 400 grams, and that's about half of what we need. Some fine soil is clouding as I pour this, but I'm pouring as slowly as possible to avoid that. We're at 727 grams now, so I'll add a little more. Alright, we have 800 grams of soil. It's important to take a mental note of this so that we can see how much soil is left on the large pan when we scoop it up later. Now, Heba will take this soil and evenly and slowly pour it into the riffle box. This box sends the soil to both sides to randomly sort the sample for us. We can see that as carefully as Heba is pouring, there's still a lot of dust clouding up. This is where we can lose precision throughout the lab. The riffle box splits the soil into 2 separate samples for us. The reason this is important is that the random sample helps us get a more representative look at the soil type. Otherwise, engineers taking grab samples will often grab what they think is representative, and this may skew the rural distribution. But engineers would never pick out soil just to make the sample fit their opinions. We're so close. 801.
Let's remove one.
Okay, we're gonna pick out the 800 grams!
Woo, winner!
So, to make extra sure that these samples are random, we will also quarter these halves and combine the diagonal samples. We want to get approximately, and I really mean approximately, half of the original 800 grams in each sample, so we do this carefully. This just makes sure that the sample is as representative and as free from our bias as possible. Heba will use a spatula to separate the halves from the riffle box into distinct quarters. After we quarter the soil, we're going to want to combine the top right with the bottom left and the top left with the bottom right. Heba will start the 6th step by using the spatula to combine these quarters. And now we have our 2 soil samples. I'm going to take our small pan that is labeled number 1 and use it to collect and measure the weight of the first soil sample. I'll zero the scale with the pan on it so that we can start with soil sample 1 from soil type 1. I'll give Heba the dustpan so that we can use the spatula to scoop the soil into the pan for the first soil sample. Because it's hard to get the soil from the large pan onto the dustpan, I'll help her out with a large brush. It's okay if we miss some of the soil though, because sample 1 is defined by what we weigh in the sample pan. However, we do want to get as much as possible to make sure the sample is, again, as representative as possible.
Wow, my God, it's exactly 400 grams. This is crazy.
And this is our soil sample 1 from soil type 1.
Yes, that's
As you can see.
That's perfect. We're so good.
Now I'm going to try to recreate the feeling of jubilation from measuring the first soil sample. I'm going to use a spatula for the first pass with the larger particles. I will carefully pour the soil into the pan labeled number 2 for sample 2 of soil type 1. I'm going to pour slowly to try not to lose too much of the fine soil from the test. When scooping out the smaller soil particles, Heba will use the brush to help me. This sample is unfortunately a little less than half, at 393 grams, so I don't feel compelled to react as if I just watched Arthur himself pull the sword from the stone. We can see that all that quartering paid off and these samples look very similar.
So we are going to start with the first sample of soil type 1, and we are going to pour it carefully into the stack of sieves, trying to avoid losing as many times as possible by pouring as slowly as possible. Then we will put the lid on to prepare for the shaker. We will open the shaker and carefully carry the stack of sieves to the shaker, place it in, and simply close the door. The shaker should be set for no fewer than 3 minutes, or the soil cannot be reasonably expected to filter down all the way. We set the dial to somewhere between 4 to 6 minutes. We will set the dial to 5 minutes for all of these tests for consistency. As the sieves are mechanically shaken, the soil flows from the top sieve to the lower sieve. On the top of each sieve, the particles that are too big to pass through are retained on the sieve. Now we are going to open the shaker and take our stack of sieves out. We will weight each sieve with the soil that has been retained. For soil type 1, sample 1. Alyssa will record the weights as I measure them. We do this one by one from top to bottom in order to make sure that we don't lose any particles that haven't fully passed through the sieves. We can catch any of these particles by keeping a piece of cardboard under the sieve as we remove it, and we can put them into the next largest sieve where they may be retained. Let me show you the first sieve. We remember that this is sieve number 4, so any soil retained here falls into the gravel category. I am careful to keep the cardboard underneath before I weight the sieve. Alyssa reminds me to put any soil on the cardboard onto sieve number 10 before I tear the scale with the cardboard, so that we can weight the sieves on this small scale. We will do the same process for each of the sieves. The soil retained on the number 10 sieve is the beginning of the sand particles. There aren't many to show right now. We will look at it later in the pan view to see the coarse particles. Here is the number 20 sieve. Here's the number 40 sieve. Here is the number 50 sieve. Here's the number 100 sieve. Here's the number 200 sieve. The soil here falls under the coarse grained soil category, but this is very fine sand. The last thing is to measure the weight of the pan. The soil here is fine-grained soil. We won't show this previous sequence for other tests in the interest of time. Now we are going to show a plan view of the sieves and what's retained on the top. Here we have sieve number 4, and there is gravel retained on the top. This is one of the key sieves we talked about that represent the boundary between gravel and sand. We can see the beginning of the sand in sieve number 10. This is very coarse sand, and as we go further down the sieves, it becomes less and less coarse and more fine. Everything retained on the number 10 through number 200 sieves is sand. We can look again at the fines. This is an important measurement, even with respect to classifying granular soil, because the presence of a lot of fines can affect the behavior of granular soil. Take a look at this particle distribution. Now, let's look at the weights of the sieves to compare. We can see the values that we have recorded. There are the first three columns that we already talked about. And in this fourth column, you can see the increased weight of each sieve with the soil retained on it. Now that we have our measurements, it's important to clean the sieves in between trials, even in the same soil type. And to reweight the sieves, we dump the soil back into the bucket of soil type 1. After we clean the sieves, we will go back in and run sample 2. You can see that some sieves have soil grains stuck in them that didn't quite make it through, and this can change the weight of the empty sieve in our calculations. So we have to re-clean and re-weight the sieves between every trial. We will only show this once for the sake of time. Now we will run the test on sample 2, soil type 1. We will again pour the soil into the stack of sieves, being as careful as possible not to lose fines. However, you can see the cloud again. We put the cover back on and then carry the sieves into the shaker. We run the test for 5 minutes again. As we can see, the distribution is very similar. However, there are some differences. You'll need to draw a particle size distribution curve for both the person passing you calculate in sample 1 and sample 2 for each soil type. This way you can see the slight differences due to procedure and random sampling. Then you average the person passing values of both soil samples to get a third curve, which represents the average curve for soil type 1. Using the third particle distribution curve, you can calculate the values needed to characterize the soil type through the unified soil classification system. When you touch the fine soil, it feels like dust or flour and sticks to Alyssa's glove. You can't identify the individual soil grains with the naked eye. Looking at the data sheet for sample 2 for soil type 1, you can see that the numbers are very similar but not exactly the same as in the first sample. Right now, we are going to move to soil type 2. We are going to take another 800 gram sample with the same procedure we did for soil type 1. First, we tare the scale so that we can pour the soil directly into the bowl. We'll be careful to avoid clouding of fines. We are about halfway through, so I'll get another scoop. We finally reach 800 grams. Great! Now we will use the refill box again. Do you want to do it, Alyssa?
This time, Heba is going to let me take our 800 grams of soil type 2 and use the riffle box splitter to split the soil into 2 random samples again. I'm going to slowly and evenly pour this, so you can see it go across the box. I want to make sure that no fines cloud up, but we can see that it is a lot less cloudy this time. Alright, I'll now make sure that everything is out of the riffle box splitter and move it out of the way. I will take the spatula to separate the halves into quarters, and I will try to keep them pretty far away from each other so that they don't mix.
The soil sample can actually smell fierce, so you want to make sure to stay as calm as possible in order to make sure that it doesn't mix. Otherwise, you'll be in for trouble.
So this is soil type 2 sample 1 and soil type 2 sample 2. And we're going to take soil type 2 sample 1 and weigh it in this pan. Then I will measure the soil type 2 sample 2 in the second pan. Heba will again record for soil type 2 sample 2, and she'll show us that the sheet matches the right sample, and then we will record the original sample weight.
Now we are going to take our soil type 2, sample 1, and pour it into our stack of sieves carefully. We make sure to put the lid on and then put it into the shaker. We run this test for 5 minutes and we'll get to see how the soil is distributed.
We are going to look at the distribution of particles after running the first sample of soil type 2 through the shaker. We can see here that the number 4 sieve is empty, so there's no gravel in the sample. It may look like there is a little bit of soil in there, but as we talked about earlier, these are just the pieces that have gotten stuck over the years. The next 2 sieves are actually empty as well, and it is not until the number 40 sieve that we see even a little bit of soil. And we can check the weights in the datasheet to be sure. There's a lot of soil in the next few, and there sure is a lot in the number 100 sieve. Let's see what's in the pan. How does it compare to the first soil type? The soil retained on the number 200 sieve may look similar to the soil that passes through, but when I touch it, it does not feel like flour, and it does not stick to my glove like Heba noticed earlier. You can see that the marks I leave behind are different, and the soil slides into this triangle trench shape. Looking at the datasheet, we can confirm that the first 3 sieves were actually empty with no weight retained. It also checks out that the 100 sieve has the most soil. I have soil type 2 sample 2 now, and I'll carefully pour it into the stack of sieves for our final test of the day. I'll go slowly as always to minimize the clouding of fines. I'll make sure the lid is on the sieves, and I'll carry the stack to the shaker. It's not too heavy, but it is a little awkward to put in the shaker. We'll close the door and we'll run the test for 5 minutes again. Looking at the sieves for soil type 2 sample 2, we can again see that the first 3 sieves, starting from the number 4 to the number 10, and the number 20, are all empty again. The number 40 has some soil, the number 50 has a little bit more, and the number 100 has a whole bunch. The number 200 has some, and the pan has about the same as it did in the last sample. Looking at the data, this checks out, and these numbers are super similar to the numbers from the first sample of soil type 2.
So now we can move to analyzing the results. For each soil type, we will have 2 samples, and thus 2 data sheets. As you can see here, for soil type 1, we have data sheets for sample 1 and sample 2, with the mass recorded for both of the empty sieve and the mass of the sieve with the retained soil. We know that in order to plot the grain size distribution curve, we need to get the percent fine, which represent the cumulative percent of the soil passing from each sieve. So first we need to calculate the mass of the retained soil. This can be done by subtracting the mass of the sieve plus retained soil from the mass of the empty sieve. This should be done for all the sieves we have. As a check, we should calculate the sum of all masses retained and make sure that it is within 1% discrepancy from the actual mass we initially weighted. Next, we need to calculate the retained soil by mass as a percent. This can be done by dividing the mass of the retained soil by the total mass. This should be done for all of the sieves we have. As a check, these numbers should add up to 100. Afterwards, we need to calculate the cumulative retained soil by mass in percent. This can be done by adding all the masses retained on the top of each sieve. For sieve number 4, we only have 19.95%. For sieve number 10, we will add the soil retained on the top of sieve number 10 to the soil retained on the top of sieve number 4. For sieve number 20, we will add the soil retained to sieve number 20 to the soil retained on the top of sieve number 10 to the soil retained on the top of sieve number 4. We should do this for all of the sieves we have. Next, we need to calculate the cumulative passing soil, or the percent finer. This can be done by subtracting the cumulative retained soil from 100. We should do this for all of the sieves we have. Afterwards, we should do the same calculation for sample number 2. After finishing our calculations for sample number 1 and sample number 2, we will have our percent finer and sieve diameter, and we can use them to plot the grain size distribution curve. For the grain size distribution curve, we use a semi-log scale. We will have the grain diameter in millimeters on the horizontal axis and the percent finer on the vertical axis. You will have two curves, one for sample 1 and the other for sample 2. You should be able to compare and provide comments on both curves. Afterwards, you will average the percent passing from both samples to provide a unique curve. You should use this curve to classify the soil according to the Unified Soil Classification System. You should be able to calculate key parameters as the passing from number 40 sieve and the passing from number 200 sieve. You should also be able to calculate D10, which is the effective diameter, D30, and D60, and use them to calculate the coefficient of curvature and the uniformity coefficient.